record, and it takes a little while when it's a kind of a long recording in YouTube to just to get compressed and get it all set up and stuff. It does take a little while and converted. So it may take a little bit if you're wanting to look back through some of the things I'm going to do. I'm going to do several problems today as part of the plan. I want to start with just saying hello to you all. I really appreciate everybody coming out the way you have. That's a good sign. It's really solid. I'm going to try to, again, keep it from being a super long class. I know it can get at the computer for over 40 minutes is a little bit of a challenge, but I want to work through a few things. Before I get started though, I want to explain something about the homework problems and the points totals. If you ever look on the syllabus again, where I had set it up, sapling is included in the point values in some way. You know, there's homework for each test section, and it's going to be 20 points for each test, 20 points for each section. And again, for this test, the first 10 points that come from chapter 1 sapling problems, homework problems, all the chapter 1 homework problems, you've got credit for, okay? It's meant for you just to experiment, get the system down, figure out how to use the keyboard, the combination of different things, make sure you're confident with the situation and how to select correct answers, and make sure you use notation they're asking for and everything. Okay, but now chapter 2 will be points that I will ask you, you will be able to get credit for. And I want to explain how I'm going to do that. What I've got set up is the idea of if you get 70% of the problems completed, you will get full credit, okay? So in chapter 2, there's a couple things I'm going to do from 2.3 and I think 2.4, but the homework problems are basically going to be 2.1 and 2.2. There's 30 problems there, all right? So if you get 70% of 30, which is 21, if you do 21 of the problems correct, then you will get a full 10 points, all right? In every section, it's going to be like that. So the idea is 70%. If you get 70% done, then you'll get the full credit for it. Again, chapter 1 stuff, you've gotten full credit for. Also, if you go on into other things and look at other things that I've put out there, things that you can guidelines, I think there's some different things available that they've put out. If you look through stuff, there's no point value to that in the course material, okay? If you want to go look at it, feel free. Some of it's very clarifying. Some of the guidance of taking you through dynamic software they use, they guide you to use it and stuff. But if you don't use that, it's no mark against you. And if you use it, it's not extra credit. It's mainly there to get an understanding of the material. That's the situation. The homework problems is what's going to count, okay? Homework 1.1 homework. Well, you've got full credit for 1.1 through 1.5. 2.1 and 2.2 you'll need to get credit for, okay? So you'll need to do those, and I'll get those up very soon. I'll probably get those out tomorrow. But today I want to go back and talk about a few other things here. Anybody have any questions at all? Make sure I'm seeing that all of your microphones are off, okay? So if you're thinking that you're saying something to me, I'm not hearing it, all right? So make sure you check that before you try to respond if that's the situation. So on my end, I've got you unmuted, but on your end, you're muted, and that's totally fine. That's good while I'm talking to have the mutation. But if you're the mutation, but the idea is if you want to say something, know that I can't hear you, okay? All right, one other thing I want to mention is, okay, so the sapling grade. Good. Also, a reminder that I am recording this. Some of you just came on. This is being recorded. So if that is an issue at all for you, make sure you let me know, or just know that it's happening. What I want to do, I want to point out a couple things. I want to go to sapling here, the text, and I'm going to look at, I've got this open here. All right. And it's, I know it's challenging sometimes to watch me work through getting things squared away here. I'm going to make sure our new share that you've got sapling on your screen here. Okay, desktop is what I want. and share. So I believe you can see the sapling book here. Is that correct? Could somebody just give a thumb? Okay, good, Matthew. Thank you for the thumbs up. Also, I've got chat open on now, okay? I'm looking at that. Several of you were making comments yesterday. I was trying to get things set up and stuff, and I wasn't really paying attention to it. Sorry about that. And so chat is open. If you've got a comment you're wanting to make, I will note that and verify that and make sure acknowledge you in that respect. So make sure you are going there if you've got something to say and not wanting to interrupt me. One of the things I want to point out is this. If you notice notice the P chapter is preparing for calculus. Chapter 1 is limits and continuity. That's getting you set up for the calculus stuff, all right? And then the word derivative shows up in chapter 2, chapter 3, and chapter 4. And then integration hits in chapter 5, and we'll go through, I'm intending to go through chapter 5.5. But the key point I want to make is the fundamental theorem of calculus. You know, I was surprised when I found this out. But the fundamental theorem of calculus, it seems like it's fundamental. It seems like it's core. It seems like it would show up, you know. Where do you suppose it shows up in of these chapters? Yes, I heard you. Chapter 5. It doesn't show up till chapter 5. Section 5.3, the fundamental theorem of calculus. It isn't until the end. It's a trip. Getting all the derivative stuff and getting the workings of it sets you up for the fundamental in use of calculus. It's kind of a interesting little arrangement there. I thought that was interesting. It surprised me when I thought about it and put the information out. Where does the fundamental theorem of calculus come in the course? At the end. What a trip. Okay, so what I want to do is this. I want to go to some of the sapling problems, if you don't mind. So what I'm going to do is go to it's a problem set, and I've got it in, I've got it in student mode, so the answers won't be shown here. What I want to do is I want to go back to section P2 homework, okay? There's a few problems here I think show some algebra skills that you're going to need for the course here. And I think it's number 10 is the one I wanted to start with. Okay, so I hope you're all able to see a graph, and you can kind of tell it starts going down when you go to toward negative infinity, and it's going up when you go to positive infinity. So what side of function is that? You remember that? You know, when you look at a graph, to be able to get a feel for what that is, you know what a parabola is, it's quadratic. What does this one look like? Okay, well, it's the cubic function is the idea. The fifth power, an odd number, odd power would be a good answer, but a cubic looks like that when you've got the convolutions inside of different zeros that can happen in things, then you get the curviness. But y equals x cubed is just, it's a s, it's a backward s type situation. It's that type of an arrangement. It's starting down left and going out top right. Also notice, which is it's a cubic kind of thing, odd number, and notice it's negative down here as you're going to negative x. The x is negative value, and the x positive value, it's going this way. That is how x to the third power looks, So it's positive x to the third is a good hint about what the end result of this problem should be. You should end up with positive x to the third as you're in your lead term of the polynomial. So let's look at this. So I just want you to remind you of this stuff. Remember that if you've got an even power, these are three factors that are given for this function. And there's more than one correct answer, but it's saying, so let's rule some out. This has got an x squared. Do you remember what that means? Also, x minus 1 is squared. So the root, the thing that causes this to be equal to 0 is positive 1. So at positive 1, we've got a 0 here. And if this was a factor, remember what that 2 does. It causes it to bounce off, okay? It would be looking like a parabola kind of there at 1, and it doesn't do that. So this is out. Also at x is 0, it would also be upward in that sort of a fashion. But notice the next one, the second one. We've got 2x. Okay, so this is, like I said, we got positive, positive, x, positive x, positive x. That's positive x to the third. That's consistent with the look, okay? That's straight. And then also, we've got to the first power in all three cases. So this is one way. It's not going to look exactly like this, but it goes up through at 0, comes back down at 1, and goes back up at 2. Okay, and that one works. So that is a good solution. Look at the next one. Bounce off, nada. Okay, and this one, we've got, this one goes through when it's a cubic, but remember, it doesn't go through straight through. It kind of looks like x to the third power. It's got a little bit of a lap to it. You know, it's got a little bit of a delay as you're going through when you get a higher power like that. So that's out. This one here, we've got a negative. So that makes you think, huh, that's not it, it's the opposite sign. But look here, we've got a negative on this x. So what's the lead term going to be in this function? Negative 2x times negative x, that's positive 2x squared. And then we've got times positive x, so that's 2x to the third power. It's x to the third power, so even though you've got a minus sign here, these two being switched, remember that this is the same as a minus sign out of front of x minus 1. It switches the two. That's an algebraic thing. Just get these tricks back going on your head. And so this is also a good solution, because if you look at it, these are actually the same thing. You have the minus sign here. If you multiply this minus sign, this, it switches the x minus 1. You get the exact same answer. And then the last one, notice what you've got. You've got the 3 zeros, 0, 1, and 2. But this one is negative. So you end up with negative x to the third. So that means it would start coming down and then end, coming down. It starts up in the negative area up here. And then it comes down, and then it ends going down this way because it's got a negative x to the third power. Okay, so try that out. Make sure you take a look at that. I think it's a good one. The next one's got something to it also. I want you to check out, I want to check out a few things. I've got a time limit I've got set for me. I want to make sure we hit the in-class problem, plenty of time for it. So I'm going to kind of move through these quickly now. Okay, find the domain of this rational function. All right, domain. So where does the restriction happen? Are there any square roots? No, that can't be negative. We do have a denominator. And if that denominator can become 0, we've got a value that the domain, that can't be in the domain, because the denominator cannot be equal to 0. So the whole thing, looking at this one, it appears that the only restriction we've got is right down here, and that's at x plus 6. So at x minus 6 can't happen. So interval notation, the idea would be to show parentheses, and if it's going from negative infinity up to negative 6 is what I want to put here. So I want to put negative sign infinities down here somewhere. Where is it? Anybody remember where that is? Forgive me, I haven't been in here in just a little bit. Infinity is in here. Negative infinity.
Look to the right.
Where is it?
To the right.
Oh, yeah. Got it. Negative, thank you. Comma, negative 6. And okay, so that's the first half. At negative 6 is the problem. So to the left of negative 6 is in the domain, and to the right of negative 6 is in the domain. So in both cases, and we got to get a union here of two sets. So the idea is we're starting at negative 6, and notice we don't include it, so we use the open parenthesis. And remember also, it's an open bracket. And then when we got positive infinity out here, infinity always has the open bracket. Never a closed bracket on infinity, because it's not a finite number. So the solution would be this. All right, that would be the answer. And get used to using that kind of notation type stuff. And then the x-intercepts, it's saying use symbolic notation, x-intercepts. Okay, so look at the two different intercepts here, x-intercepts and y-intercepts. Anybody have a pattern in your head how you find the x-intercepts real fast?
X equals 0.
Okay, so you set the opposite equal to 0, right? So if you set x equal to 0, what happens there is when x is equal to 0, that means you're on the y-axis. When x is equal to 0, you found the y-intercept. So when x is equal to 0, if we plug in 0 for x here, we get 0 over 6, which is 0. So the y-intercept occurs at 0. All right? Now the x-intercept, you got to make y equal to 0. And when you're first coming back on stuff, remember this now. What will cause y to be equal to 0 in this function? Y is this r of x. The y-axis, the dependent variable is over here, and what causes it to be 0? The denominator doesn't, okay? But so if you make the numerator 0, you've made y 0. So whatever causes the numerator to be equal to 0 causes y to be equal to 0. So the x-intercept, the only one that there is again when you plug in 0. So 0 would be the solution here, okay? And it looks like the answer, give your answer in the form of a comma separated list if needed. So we have 0 here is the only x-intercept, and the y-intercept, the only y-intercept is 0 also, isn't it? I think that's right. So I'm going to check the answer now. And it got it. So get the idea there. That's the situation. Okay. So any questions about either of those? This is meant to be a reminder. Look at the rules. It goes through that. Look at 12 here now. This is kind of important, you guys. I want to hit this too. I'm going to move through quickly because I've got to move on to some other things. So find the domain of the rational function. The domain. So what values can work? Again, is there a square root? No. So that is not an issue. Is there a denominator? Yes, there is a denominator. Can you make it 0? Whatever will make that denominator equal to 0 is not in the domain. In this case, you've got x squared plus 5. This is when you got to get back the rules in your head. This is not factorable. It's the sum of squares, and 5 isn't exactly a perfect square, but it's the sum of two values. If you had the square root of 5, you look at it that way. But that is not factorable. The difference of two squares is factorable. That's the next one. We can do that. But in this case, the numerator, the domain, is there's no restriction on this. No number you plug in will cause there to be a problem. Therefore, negative infinity to positive infinity will be a good answer on this one. X-intercept. What causes this? So for the y-intercept, I said x equal to 0. I get 0 minus 0 over 5. That's 0. So the y-intercept is at 0. The x-intercept, what causes y to be equal to 0? Y equals 0. It's the numerator. This is factorable. It's got an x common. I can take out an x here and get 7x minus 1. And therefore, whatever causes this function, I get 7x minus 1. And whatever causes one of those two values to be equal to 0 are the x-intercepts. So you end up with what? 1/7 and 0. So we'll talk about that, take a look at that a little bit downstream. I want to go to the next one. There's something else I want to get to that's a little bit more significant here. This is kind of important to look at diagrams. I'm going to move through this quickly, and if you have issues, go back to this problem and look at it yourself, okay? It's number 13 in problem set 2. But the question is saying, what's the formula for the area of the rectangle as a function of x? Okay, so all you're given here in this function, if you were asked just come up with a formula for the area of this rectangle, notice what it would be. What would be the length of this side of the rectangle? Think something to yourself. Okay, notice this would be x on this side. This is the exact same distance. So this side would be 2x. And what's the y? Well, what's the height? It is the y value, whatever it is. So it's going to be 2x times y gives you that. But it said, this question is saying, put it as a function of x. So what we need to do is change the y to be a function of x. I'm going to change it to my iPad in just a second here. But and we'll show that. I tell you what, time-wise, I'm going to come back to this another time. This isn't getting into questions I'm going to be asking soon, but it's a reminder to you. You got to solve for x. Remember, the formula for a circle is x squared. If the origin is at 0, 0, the origin is the center, then x squared plus y squared equals r squared is the formula for the circle. And the radius is 8. So x squared plus y squared equals 8 is going to be the deal. 8 squared, excuse me, x squared plus y squared equals 8 squared, 64. Then you got to solve for y. So you subtract the x squared, take the square root, take the square root to get the y by itself, and you'll have the formula, okay? And the perimeter here, notice this. The perimeter of this is going to be equal to what? It's this plus this. This is x. The perimeter is 2x on this side. So I got to get both sides if I'm doing the perimeter. So it's going to be 4x plus 2y. So whatever formula whatever you come up with to get y, when you solve for y in that previous problem using the formula for a circle, you end up getting a radical. Y equals the square root of what, 64 minus x squared, I think, would it end up being? I think I said that off the top of my head. Excuse me. It's a recording, so it's going to keep going. But anyway, take a look at that. There's some notation that we're going to use later. That's a good review of some things. Now, really quickly, I want to talk through something else here from section 1.1. So I'm going to go to section 1.1 right now, the 1.1 homework. Homework 1.1. So the homework 1.1 through 1.5 are the, that will be counting, and you've gotten full credit for them. Now, the reason I picked this one is because these early problems is because they are simple, okay? Because this is it says the formula is 2x. So that means you have to multiply each of these numbers times 2 to get your answer, okay? That's not challenging as much as the second one, it's addition. So you just take this number and add 3 to it and fill in the table. And that's what it's going to. This last one I left in there just to remind you that this is chewy, okay? So you've got e to the negative 0.2 divided by negative 0.2. That's going to take a couple minutes to do each of these. E to the negative 0.1 to the negative 0.01. And when you calculate that, it takes a little bit more work. I left it in there for this problem set because sometimes math is that way and you got to do it, that kind of work. But in order to get all these answers, you got to plug this value in for x in the exponent and the denominator. So that's just meant, you want to take it, do it, that's fine. You can also look at a graph and get the answers. Again, you've got full credit for this question already. So it's not one you have to complete. Okay, but what I wanted to do, I wanted to look at number 10, 11, and 12. Okay, piecewise defined functions. And it's asking at the numbers, find the limit at the number c. And in this situation, it's saying the limit. So as you approach from the right, you're coming in where x is greater than 3. As you're approaching from the left, you're coming in as x is less than or equal to 3, less than 3. You're coming in from that side. So plug in 3 to each number, and if it turns out they're different, then it's not defined. Otherwise, you get the answer whatever you plug in here. Plug in 3, you get 12 plus 12 is 24. Plug in 3 here, you get 18 plus 6 is 24. So the limit is 24. That's the situation in that case, okay? And so it is a matter of, got it. All right, now look at the next one. Okay, so at c equals 1, I plug in 1, I get 12. I plug in 1, I get 5. This one, it doesn't exist because they've got to be going to the same place. From the right and from the left. If they're going to 2 different values, then it does not exist. So D and E would be an appropriate answer here. D and E. Okay, check answer. Okay, got it. Okay, so now look at the next one. There's 3 of them. Plug in 1. Are they all, if they're all the same, then everything's fine. Plug in 1 here, I get 1 plus 5 is 6. 6. Plug in 1 here, I get 5 minus 1 is 4. Does not exist. Okay? So that's not, it doesn't go to the same place. This one I wanted to show you also because we haven't talked about this in class or in specific problems, but notice it's asking for the average rate of change. This is meant to be a review for you. The average rate of change means how much has it changed over time, which is the change in y over the change in x. Rate of change has got to do with slope, okay? And so the idea is, if it's talking about the interval, notice what the question is asking here. Find the average rate of change on this interval. So you want to find the change in y over the change in x. And the change in x is going to be 3. The change in x is 5 minus 2, or 2 minus 3, whichever way you do it. But you got to stay consistent. If you take 5 minus 2 on the bottom, the change in x, then you need to do 5 minus 2 on the bottom. Well, you need 12.61 minus 4.21 on top, okay? So you got to make sure you do that. I could also do 2 minus 5. That would give me minus 3 on the bottom. And when I do this subtraction, I got to do 4.21 minus 12.61 and get that average rate of change by staying consistent. You just got to keep the order the same, okay? That was a key point I wanted to do. And then I want to say something real quickly from 1.2. Any questions on either of those so far? Okay, I want to look at this. Number 11 was something here I wanted to hit. If you got questions on it, going back over these would not be a bad thing to do. Wouldn't be a bad move. Okay, so here's the situation. Let me do this problem right now. I'll do it on my iPad. The idea is, what's the limit as x goes to -7? Right now, you plug -7 in, and you get 0 in the denominator. That's the key problem. So if I'm looking at number 11, it's question 11 from section 1.2. And it's the limit as x goes to -7, x goes to -7 of x plus 7 over x squared minus 49. Difference of two squares. I hope you can see right now that that's a difference of two squares here, okay? That's x plus 7, x minus 7, okay? So rewriting this, you keep the limit. If you were asked to write the situation out, you would end up with x plus 7 on top and x plus 7, x minus 7 on the bottom. And it turns out that these would cancel, and you end up with 1 over this. And the limit as x goes to -7, then now there's no problem. If I plug in -7, I don't get 0 in the denominator. So now just plug it in and get the answer. I get 1 over -7 minus 7, which is -14 down there. So the answer is, remember, the minus sign doesn't stay in the denominator. It's either out front or in top, the way we've accepted our mathematical notation, -114. So the idea of factoring it, canceling it, that means in the graph, if you have it on your TI or if you have it on Desmos, at x equals -7, there's going to be a hole. This is a line. The graph is going to be this function right here. That's what it's going to look like. Plug that into your calculator, and it'll look exactly the same as this.
Bob, we can't see your iPad.
Go ahead.
We can't see your iPad if you're intending to show us what you're doing.
Oh, no, you're right. You're right. Okay, so good. Let me come back and do that. Thank you for speaking up. Okay. No, that's good. Okay, so let's look at this. I see a couple of your notes here about iPad and a combination of things. Well, I'll answer those questions later. But here's the idea. So if you have the limit as x goes to -infinity of this function, that's the same as that. This is the same as, you can factor the denominator. This causes a problem. You plug -7 into the denominator, and you end up with 0 down there. So as long as that's happening, you can't plug in -7 into the function. But if you factor the denominator into x plus 7 and x minus 7, now you get the x plus 7's cancel. Now you plug in -7, and you don't get 0 in the denominator. So this is the answer. And that's saying where the hole will be in your graph. The curve, this curve right here, is what the function looks like. All right? When it was on top, it would have been just an equation of a line. You've got it in the bottom, therefore it's going to be a curve, but it's going to have a hole at x equals -7. If you put this function on your calculator, the x plus 7 over x squared minus 49, and you drag your cursor across the curve, and when you get to -7, it's going to be a hole there, okay? So that's the main idea I wanted to point at there. Let's go on to a couple more. I want to make sure I have time to get to the problem that we're hoping to get to. Let's do I want to show you number 12 also. No, 15. That's 12, 15 had something about it. Okay, so this one's coming from the left and from the right, and it's asking, is it what it is, and then it asks you for the limit for this situation. So if these two limits are exactly the same, oh, you're not there yet. Okay, good, good, good. Thank you. I heard the vibe. Thank you, thank you. Okay, I've looked at number 15 now. This is number 15 in that problem set. Okay, so now it's saying you've got x coming in from the left of 1 and x coming in from the right of 1. If those values are the same, then that is going to be the answer for x, the x going to 1 period. If you plug in 1 here, you get -3. You plug in 1 here, you get 4. They're not going to the same place. The limit is not defined. It does not exist, okay? Because they're going to 2 different places. So from the left, plug in 1 to the one that's coming in from the left, less than 1. Therefore, plug in 1, you get 2 minus 5, which is -3. Answer. So you get -3. And then the next one, if you notice you come in from the right, you hit this one, which is 5 minus 1, which is 4. All right? Those are not the same, and therefore DNE is the end result. All right, so check that out yourself, hit that problem. I also want to do number 16. I had 16 listed here. Yeah, let's do this one kind of quickly, and then I want to go on to some trig things. Then I want to hit the problem set. So look at number 16. This one, if you haven't done one like this before, I'm going to my iPad now. Let me write this down. Limit as x goes to 40 of x minus 40. But you can see the 40 is going to cause the numerator to go to 0. Does it cause the denominator to go to 0? Yes, it does. Because of the fact that you add 40 to 9, you get 49, and you get 49, and the square root of 49 is 7, and 7 minus 7 is equal to 0. So the situation is, let me go to new share. Let's go to my iPad. Okay, so here's the problem. Pardon me if that's chicken scratch a little bit. I hope you can read it. But the idea here is that, does this cause the denominator to be equal to 0? Yes, it does. And later on, we're going to find that there's a rule that we can use. L'Hopital's rule is coming downstream, where if you've got, this is called an indeterminate because the top and the bottom both go to 0. And so you can use a L'Hopital's rule and simplify this problem kind of quickly and get what the answer is to this without having to do what we're going to do. But for right now, what we're going to do is just check it out. Can we plug in 40 to this? No, we get 0 in the denominator. So what I'm going to do is I'm going to factor the bottom. Notice again, the idea is difference of 2 squares, okay? And what we've got is we're going to want to, if we multiply by the conjugate by plus 7, then you multiply those two together. Remember, if you've got a plus b and you multiply it by a minus b, or vice versa, whatever, you get a squared minus b squared. So that term is going to be squared. And if you've got a radical, you're going to square it. That radical is going to disappear. And there's no middle term to worry about. There's not going to be a radical. So what we've got to do is redo this. I'm going to multiply the top and bottom by the conjugate, which is the same thing that I want, that's got the radical here. I'm going to multiply this by the square root of x plus 9 plus 7, all right? And I'm going to multiply by the square root of 9x plus 9 plus 7. Top and bottom, therefore I'm multiplying by 1 here. And now I've got 2 terms on the top, x minus 40 square root of x plus 9 plus 7. Now on the bottom, I've got this term squared, which is just going to be x plus 9 now, minus this thing multiplied out, right? This times this, so that's minus 49. Okay, so now the purpose of doing this is to see if I can get some cancellation, and typically you do. Notice we've got x plus 9 minus 49. That means I'm going to end up with x minus 40, which I have on top. So I end up with x minus 40 on top times the square root of x plus 9 plus 7 over x minus 40. Same as cancel. Cancel. Now, if I plug in 40, does that cause a problem? So, excuse me, you know what I did here? I did something I'm going to flag you guys on. I'm going to take off. So if you see that you've done this up to this point, from now on, this limit, we have not plugged in the 40 yet. Therefore, that limit symbol needs to be there. Therefore, the limit needs to go here. And what I'm going to say we can do, you can use a smiley face, okay? If you just use a smiley face in front, then that will be evidence that you recognize that's the limit symbol, okay? Whatever that is, you can use that in that fashion. And now we've got the limit as x goes to 40 of the square root of x plus 9 plus 7. Now I can plug it in. So now the limit symbol is no longer needed. I plug in the 40 and I get the square root of 49 plus 7, which is 7 plus 7, which is 14. So this original problem, it turns out to be the limit is 14. Plug it into your calculator and you'll notice as x goes to 40, near 40, there'll be a hole. And it'll be at y equals 14, okay? Any questions come up about that? Okay, let me say a couple things about some trig things, and then we'll go to the problem that the ICP, the in-class problem that I'm hoping to work with. So I want to hit from some trig situations. Let me do this. I've got a screen set up on my iPad. Remember this, okay? I'm going to kind of move through this kind of quickly, so I hope it's a review for you. If you already know it, then just smile and keep going with it and be patient. I'm going to go to some in-class problem in just a second. But here's what I want you to recognize. The trig functions. Remember, trig came from, the key word is the first letters here, tri. It came from a triangle. Right triangle is our typical situation of trigonometry. And remember, the SOHCAHTOA is something you've probably come across in the past. And remember that sine, remember what these stand for. It's the symbol for what each trig function, how it's defined on the triangle, the right triangle. And that sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. And tangent is equal to opposite over adjacent, okay? So in this triangle right here, I'm going to come back here. Remember that it's based on the unit circle. It's based on the unit circle, which means the unit means the radius is equal to 1. R equals 1. So on the unit circle, the values of the functions are based on the radius of 1. And if you notice that the y is the y direction is up here and the x direction is over here. And remember, x stands for cosine and y stands for sine function, the sine value, okay? And on the unit circle, remember this, that as you go around, if we've got the sine of, let's say we're at 45 degrees, which I have here, which is halfway, 45 degrees, that is, the sine is opposite over hypotenuse. And so it turns out to be the sine is going to be equal to y over 1. And dividing by 1 each time is what the simplified aspect of this thing is. So it's just going to be, it turns out to be, and we got a 45, 45, 90 triangle. It's the square root of 2 over 2. Square root of 2 over 2 are the two coordinates, the sine and the cosine. Do it on your calculator, you get that value. But in the cosine, if you notice, is the x value over 1. Cosine is adjacent x over 1. And it turns out to be square root of 2 over 2. And we can do the math and figure that out another day. The key thing I want to point to is this. The graph of sine and cosine is what I want to go back to. And it comes from this. On the unit circle, remember the coordinates here. At 0 degrees, and typically in math, they use radian format, okay? So 45 degrees turns out to be, remember, this is 180 degrees over here. And that turns out to be pi radians. That turns out to be, we'll talk about that on another day, but it's 3.14 radians. The length of the radius, 3.14 times. It's kind of a neat moment. Talk about that later. This is pi, but this turned up as half of that, turns out to be pi over 2, and this 45 degrees would be half of that, that's pi over 4. So that would turn out to be pi over 4 radians for that angle. 45 degrees is pi over 4 radians. Okay, but the key thing I want to point out is the graph of the function. Okay, so we've got, if you notice, the cosine is the x value. The sine is the y value. So let's look at the y value as we go around the circle. At 0 degrees, which is 0 radians, the y value is 0. So I'm going to go to this table here. The sine at 0 degrees is 0. At 90 degrees, we go up here, well, that's pi over 2. Notice what the sine is. The sine is the y value, that's 1. At 180, we're out here at pi. The sine is 0 again, the y value. And down here, the y value is negative 1. And then you go back up to 360 at 2 pi, 360 degrees, and that turns out to be, again, 0. And then the cosine, let's go around the circle. The idea is the x value at 0 is 1. At 90 degrees, the x value is, the cosine is 0. At 180, we've got negative 1 at pi. At 3 pi over 2, we've got 0 again. And then at 2 pi, we're back up to 1. Okay? So if we go to look at the graph, as a reminder, this is what we're talking about. The sine value at 0 is 0. At 90, at pi over 2, it's positive 1. Remember, the values can only be between 1 and negative 1 when you're talking trig functions, so sine and cosine. Sine and cosine are only between 1 and negative 1. That's got to be. Okay, when you get to pi, we're at 0. When we're at 3 pi over 2, we're at negative 1. And when we're at 2 pi, we're back up to 0. And that ends up giving us this curve. And again, it would come down here like this. Okay, and it goes on again. It doesn't stop at 2 pi, but that's the general shape. And the big thing is noticing where it crosses the x-axis. The big thing, okay? Look at the cosine now. Cosine function, let's go down here. At 0, it's 1. Starts up, away from the x-axis. Also at 90 degrees, pi over 2, we're at 0. At pi, we're at negative 1. At 3 pi over 2, we're at 0 again. And at 2 pi, we're at 1. And again, if this is old news for you, I'm glad. That's good. But if it's not, take a look at this, look things up and be confident with it, get comfortable with it, because we're going to use things from it downstream. Notice the sine starts at the origin. It's on the midline. It's called the midline, the halfway point between the top and the bottom. The x-axis, where is that? It's at 0. Sine starts at 0. Cosine starts off the midline. It starts up off that base. So that situation is remembering that of the graph, okay? One other key point here, there's one more thing to make note of in the text, and we'll hit the problem in just a second, the in-class problem, okay? I just want to say this one more thing. This is going to show up in the text. They're going to do a proof of something using this point in just a second. The graph of, this is an important one that's used in calculus in a couple different ways, but the limit as x approaches 0 of sine of x over 0. Notice if you plug in 0, you get sine of x at 0 over 0, but the 0 is, it's in the denominator. That means it's not part of the domain. So that means you are going to have, when you graph this thing, there is going to be a hole in this graph, but where is it going to be? The thing I wanted to point to is that this is the graph, what it looks like. Go ahead and you can plug that into your calculator. The graph of this function, sine of x, if you graph this function in your calculator, you see it comes out like this, okay? The point I want to make is this right here. At 0, it doesn't fly. It's undefined. So there has to be an open circle. There is an open circle there. So one of the situations that happens, notice where it's going when it goes from the right or from the left. Notice where it is approaching. As x approaches 0 from the left or from the right, it's approaching 1. So, and we can prove that mathematically, and they do it in the book a little bit, but we haven't, there's some things they use that we haven't talked about yet. So that's a situation that to look at. This is an identity that is given in the text. They also mention that the sine of x, the limit as x goes to 0 of sine of x is 0. And you notice that the limit as x goes to 0 of cos x is it's up here. It's 1. All right? X goes to 0. Now, this is another one, sine of x over x. And this is a problem that they give in one of the problems. Let me finish this off, and then we'll go to the in-class problem. But here's the deal. Part of the situation is this is different than this. Notice the value of the sine is being, the sine is being taken at the value of x, and x is in the denominator. It's got to be exactly the same, okay? Well, we can't manipulate what's inside this parenthesis for the sine, but we can get that denominator to be equal to 3. And if we do that, we will have accomplished making the x value be the same for the sine, the sine is being taken out, and the denominator. So the idea here is if I multiply the bottom by 3, that means I've also got to multiply the top by 3. And the 3 is out front of the cosine, of the sine function, right? So this becomes the limit as x goes to 0 of 3 times the sine of 3 theta over 3 theta. Now I've multiplied the 3 down here. All I've done is multiply top and bottom by 3. It's a mathematical trick that is wonderful. The 3 is out front here. So it turns out that now, if I take the 3 out front, when you look at the limit definitions, this is the same as the limit of a constant times a function. If you take the constant out front, that's the same thing, right? All right, so you end up with limit as x goes to 0 of sine of 3 theta over 3 theta. This is equal to this, the limit as x goes to 0 of this is equal to 1. So this is equal to 3 times 1, and the answer to that is 3 then, okay? So getting this to be in this format, there's a couple problems in Sapling that are asking you to do that. So please, anybody have any questions on that at all?
Where did the 3 come from?
Go ahead, Cassie, go ahead.
Where did you get that 3? Why did you put it in front of the theta?
Okay, so part of the situation is, I needed to have this result right here in order to make the limit of the sine function equal to 1, okay? I had to have what's in here to be exactly the same as what's down here. I could not manipulate what's on top here. That the sign of that value has got to be set. That's a number itself. But I could multiply the bottom here by 3. If I multiply the bottom by 3, like I did here, I've also got to, in order to make it 3 theta was the goal, okay? To make it look like this. I made a mess of this now. But if I multiply the bottom by 3 to get this to be 3 theta, I've also got to multiply the top by 3. And that top by 3 ends up going out front. It ends up coming out front. I had to multiply the top by 3 in order to get this denominator to be 3 theta. So I had to introduce a 3 in the numerator. Mathematically, I had to multiply by 1, 3 over 3, okay? So that gave me the 3 in the bottom, and that 3 became extraneous. It became extra up on top, and that means it came out front. It lived separate from the other part of it. So the answer is going to be 3 times that. Okay? Everybody okay with that?
I'm kind of confused. So I understand that you're saying as x approaches 0, should it actually be as theta approaches 0?
Oh, wonderfully said. Notice, yeah, theta. Pardon me, you guys. That was a glitch.
You good.
I had this up here originally written in x, and I kept it x, and I wrote theta down here. Pardon me. So if these were thetas all the way, these would be either thetas all the way or they're x's all the way, okay? This needs to be theta. Okay, this needs to be theta. If you've got theta, I'm sorry about that. Good observation. Thanks for bringing that up. And if you guys do that, I can mark off on yours. You know what I'm saying? But notice the way I originally wrote this problem is this. I was talking in terms of x. But if you introduce theta, like I did, then everything needs to be theta. The limit's got to be going theta to 0. Theta's got to be going to 0, not x, okay? So that would be a miscommunication. If you mix your letters together, that's not good. That's not healthy. So thank you very, very much. on the two graphs I had here, I had them in terms of x. And then when I had the problem, I had it in terms of theta, so I blended them together. You got to be able to catch that. Make sure you stay consistent. So thanks for speaking up, Thomas. Very good. What's the cat's name, Thomas?
I don't know. My instructor was teaching a class. I took a screenshot and made it my screen.
Okay. Well, listen, you guys. Here is what I want to do now. That's it. Any other questions? I wanted you to see this, to do some problems, and to remind you about sine and cosine. Sine and cosine are going to be the major things. Tan, remember, is equal to opposite over adjacent. So tan of theta is equal to sine over of theta over cos of theta. We'll be talking about tan less, but tan will be showing up more. We're going to be using mostly sine and cosine in this course. Cotangent, cosine, secant and cosecant, they're going to be mentioned, but we're not going to be dwelling on them. Sine and cosine are going to be the major trig functions that we're going to be working with, okay? Okay, so now you guys, pardon me for taking this long. It's almost been 50 minutes, but I want to go to now, I'm going to go back to into As You Learn and open up the in-class problem, okay? So I'm going in right now. I'm going to go to a new share and go to my desktop.
I kind of got another question for you.
Say it again.
I got another question for you. If you have sine of 0, wouldn't that mean that it would be 3 times 0? So the answer to that last one should be 0?
Okay, let's go back to it. Okay, I'm going to go back to the iPad. Good. Thank you for asking. I'm going to go
Because,
back.
I mean, if you got theta equals 0, it means 0 radians, correct?
As theta goes to 0. Right. So what's happening is, so the question is, as theta goes to 0, the limit as theta goes to 0. And what we've got is, we've got 3 theta over 3 theta. And the rule that we've been given to work with is when you've got the sine of a value divided by that same value, as theta goes to 0, the answer to this, the limit, is equal to 1. So in essence, this limit is the sine of some value, angle, over that same value. That is equal, the limit of that is equal to 1 as theta goes to 0, okay? So it ends up being 3 times 1. So this ends up being, this value right here is this. It's sine of x over x. So if you've got, as long as you've got, so we could replace that 3 theta with a t, say, okay? And so it would be sine of t over t. So as long as this value is the same as this, then the limit of this is going to 1. By looking at the graph, we can show it mathematically if you want to, a little bit downstream. But the answer is, the limit of that is 1. So as long as you have the relationship that the denominator is the same as what value you're taking the sine of that angle, then the limit is equal to 1 and not 0. Okay, you hear me on that?
Yeah, I got
Okay,
that.
good. All right, let's go back now to, I'm going to open up this I'm going to go to my iPad, and I'm going to open up back in As You Learn, and you're going to be able to look at the problem yourself if you want. I've got it, so I'm showing the problem now in As You Learn. That if you select that, the problem should come up. And if you go to, this is where I'm asking you to submit your draft when you're done, okay? And right now I've selected it, and therefore it is down on the, I went to a new share. Okay, so I went to my desktop, and now what I end up with is, cancel that. Okay, let's see. Do you guys see the problem, the in-class problem 1 on your screen?
Yeah.
Okay, it's part of my full screen here. It's off to the right. Okay, so do this with me now. This will not take long. So if you've got to run somewhere, I'm sorry if this has run longer than you had hoped. But let's go to a new page. Okay, so I'm going to solve this problem now. So the idea is f of x is equal to is equal to x squared plus 6x minus 16. I'm going to go, okay, and I'm going to put this on the screen. I'm going to put the difference quotient on my screen. And then notice the second part. It says, what's the limit as h goes to 0? All right? So what we're going to do is get the answer here and then take the limit of our answer as h goes to 0. This won't take long at all now. So we're going to work through this problem. I'm going to find f of x plus h minus f of x over h. So let's go to my iPad. Let's do that now. I want to go to share screen and go to my iPad. Okay, so, and this is what we want. And then I want the difference quotient. I want to find the difference quotient, which is f of x plus h minus f of x over h. That's how it's defined, okay? This is the difference quotient. Diff quote. That is the difference quotient. So I need to plug in f of x plus h, subtract f of x, divide by h. All right? So what I'm going to do is, so I'm going to say the difference quotient then is equal to, so the diff quote is equal to, be careful because what I'm careful of is I want to make sure I'm not saying I'm equal. If I put an equal sign under here, I'm kind of saying f of x equals, that looks like it's equals this, and that's not the case. The difference quotient is f of x plus h, which means I need f of x plus h. That means I need f of x with x plus h plugged in. So everywhere there's an x, I need to plug in x plus h. This is f of x. This is f of x. Something squared plus 6 times that something minus 6. All right? Well, this has got to be x plus h. All right? This is f of x plus h. And then I've got to subtract. You guys, if you're writing this down on your paper, make sure you do it neatly. I'm going to ask you to upload it. Do it neatly so I can make it clear. Don't be scratching in and doing a combination of things. When you upload it, I need to be able to read it when I open it up, okay? So minus f of x now, like I've said before, that f of x, that minus sign minus f of x, I need parentheses around it. There's more than one term here. Every term needs to be affected by that minus sign. I'm on the iPad, right? Yeah, okay. And then this is divided by h. Okay, and now I set the equal sign up. This is the difference quotient. So that is going to be equal to, now that it's a string of equalities. Remember, you guys, make sure you use equal signs. Math, there's a lot of times people write up and students have come through and they don't put equal signs. They just put numbers down. Mathematical equivalence is an essential part of this process, okay? So this is exactly this, mathematically equivalent to this. So the x plus h, remember, this is not x squared plus h squared. We got a middle term. So it's going to be x squared plus 2xh plus h squared. You could have that 2hx also. That would be just as well. That is this. And then I've got to add to that, distribute that 6, subtract 16. And now I'm going to change the signs of all 3 of these terms. And that, I didn't need that. And then that's going to be over h. Okay? All right, now, so now I've got a string up there. All the parentheses are gone. Now I can do some cancellations. And you guys don't get in the habit of, there's going to be h's in the end. Don't go through and cancel pluses and minuses and factor out the h in the same step, okay? Don't do that. So what I'm asking you to do is do on this step, if you want to cancel the x squared and the minus x squared, this minus 6x and this plus 6x, and this plus 16 and this minus 16, that's one step, okay? And what we have left on top, there's 3 terms, and they all have h's in them. That's everything. Now, if I factor out the h, that h is going to cancel. And remember, when you finish factoring this out, the h out, you multiply it back out, you should get back the exact same thing. That's an algebra check, you know? 2xh, h squared, 6h. Got it, okay? And now I've got the factor out front, and now it's going to be canceled. And the answer to this question is, this is the difference quotient. That's 1A. Now, typically what you're going to be doing in problems, this is how we're calculating the derivative. This is the limit definition of derivative. You use this. And part of the answer, part B, look at this. I'm going to go back to the screen. I'm going to go back to this problem here. All right, and show you down here, this down here is the limit definition of derivative. So all we're going to do, those of you that have experience with calculus a little bit, if you go back to that original problem, I'm going to point out that what we're going to do now is just take the limit as h goes to 0 of that answer. So this is the answer for 1A. 1A is 2x plus h plus 6. Okay? And now what we're going to do for part B is the limit. Okay, so now I need to move this back to my iPad. Okay, so I want to point out, so a few of you have had some experience a little bit more with the math, with the calculus, and you knew with a little bit of experience by looking at this function at the top. I'm putting a box around here at the top. You can tell what the derivative is of that kind of quickly. You know, there's a power rule on top here that brings the 2 down front and subtracts 1 from the exponent. So you get 2x. And the derivative of this second term is like, what's the slope of that line? The m is 6. So the derivative of that term is 6. And what's the derivative of a constant? What does the graph of y equals negative 16 look like? That would be a horizontal line going through y equals 16. What's the slope of that line? 0.
Yeah.
Okay? You okay? Diamond, what's the question? So it turns out, if you had past experience with this before, you could see that the derivative of this function would be equal to 2x plus 6. And what I'm saying to do here, the limit as h goes to 0 of this, that's what all you need to do to answer the question is this. Plug that in, plug that function in, and take the limit of it, and now we're going to plug 0 in for h. It doesn't cause any problems. So that is going to be equal to, plug in 0 for h, and you end up with 2x plus 6. So, and with the answer to 1b, the answer is 2x plus 6. Okay? And if you notice, those of you getting with experience, you know what the derivative of this is. It's 2x plus 6. And we're going to be seeing that in just a little bit more often. These are the 2 answers you need. Come show your work, how you got it. And I'm going to ask you to upload that sometime today. If you've got it done and you want to upload it right now, you're welcome to do that. But you've got until 10 o'clock tonight to do it, okay? So if you want to go through that problem again, go work it yourself or do it on a clean piece of paper or anything like that, feel free. Doing it right now, and it's open right now for you to upload back in as you learn. So take a picture of it, make it a PDF file, and upload it, and make sure you hit the submit button. Make sure you hit the finish and submit, or whatever the finish button looks like on that, okay? Any questions now about any part of this problem?
Why did we plug in the 0 for h instead of x? Or how do you know that you should plug it in for h instead of x?
You guys, look what I did. I did it again here. Limit as what goes to 0. Go back to the initial problem. What's going to 0? H. The limit is h goes to 0. This is incorrect. This should be an h down here. The limit is h goes to 0. I'm sorry about that. Okay? I hope that makes sense now. Look at that bottom question and on the sheet itself and realize it's saying the limit as h goes to 0. And the idea, you guys, is remember on the graph that we had worked with, we had a number line and we had x over here, and then we moved over h. Okay? So this next term was x plus h. So the limit as h goes to 0, we're getting closer and closer and closer to x. So the limit as h goes to 0 is what makes it. That was a typo on my part. Thank you for speaking up, and I'm glad we caught that and didn't leave that on the recording. That should be h goes to 0. That's a crucial part of that definition of the limit definition of derivative, okay? So you saw what happened though. You see how fast I got x and h switched? Make sure you're conscious of that, okay? You can't do that. That's critical to make sure your math is true, all right? Anybody else have any other questions at all?
Is there going to be something on As You Learn for upload again? It's that same thing that we were having issues with earlier, right? The double check and the double click to submit.
Right. So if you go to As You Learn, I'm going to go there right now. Let's go there. I'm going to drop off this, okay? Anybody else have anything else you want to do? I'm going to go to As You Learn. I've got it somewhere here, don't I? Yeah, here we let's go back here. Okay, so in As You Learn now, I've got in class problem 1. Click on that. That will give you that problem set, and there will be a place for there. It's an in-class problem, and I've given you an opportunity you can upload back the file you need. Once you get a picture taken or whatever, you've got an opportunity to give a submission to that, okay? So you can make a submission there. Is that what you were asking?
Yeah, that's awesome.
Okay, good, Thomas. Okay, anybody else have any other questions at all?
How do you want us to name our PDF?
Say that again.
How do you want us to name our PDF?
How do you, to name it? Okay, good. Again, it'll be beneficial to me. Oh, I didn't say that, did I? Your last name will be helpful, okay? If you want to say last name, then first name, that's fine. But your last name and something related to the assignment. So if you just say, you just put your name on it. When you put it in there, it's going to go specifically for that assignment. So that's not going to be crucial. But it's going to be in ICP 1, okay? So if you put your last name, and if you want to put Story, your first name, that's fine. But definitely your last name, and if you want to put ICP 1 after that or something like that, that would make it very clear. So if I get multiple files together, I'll know what that is, and you'll know what it is. But your last name with ICP 1 would be helpful for you later, I think, also. Okay? And make it a PDF. Make sure you send it as a PDF. Everybody okay with? And if you're not sure how to do that, remember there's a in the beginning. I've got up on the top screen there the link for As You Learn guidelines. Has how to save it as a PDF file, a combination of different ways, and if you save it as some other file, you can convert it to a PDF file fairly quickly. If you got questions about that, let me know. Okay, so 10 points.